So, welcome to the next lecture of linear algebra. In the previous lecture, we were discussing linear first order ODEs. Today, we shall continue with the linear first order ODEs. We were discussing example 2 in the previous lecture, so today we are going to discuss example 3. If you have any question regarding the previous lecture, you can ask me. You just raise your hand and you can ask your question. So in example 3, you can see another example, which is solve the following ODE, and the ODE is x square minus 9 dy by dx. This is the general form of ordinary differential equation, first order linear ordinary differential equation. First, what we do, we have to transform it into the standard form by dividing this factor throughout on both sides. Sorry. So when we divide this factor on both sides, we get this term. You can see. Now this term becomes 0 when x is plus minus 3. So the points where the differential equation is not valid or it becomes undefined, those points are basically called singular points. So these points are the singular points of the differential equation. Now we can see that p of x is this thing with the negative, no, with the positive sign, yes. With the positive sign here, there's a typo mistake. So we can find the integrating factor by calculating this expression, which is e raised power integral p of x. You can see that after integration, we can obtain e raised power 1 by 2 log of x square minus 9. So we can take 1 by 2 on the power here, and e log can be cancelled, and we get this integrating factor. Now multiplying the given equation, this one, sorry, in this one, which is in the standard form, we multiply this equation with the integrating factor, and we can obtain simply this thing. Now integrating, we get this is equal to c constant, and we can divide this thing on the other side, and we get solution. Now you can see that this solution is valid only for these two intervals, minus infinity to minus 3 and 3 to infinity, whereas the singular points are these ones. So we can, if these are the singular points, then we can divide the set of real numbers onto 3 intervals, which is minus infinity to minus 3, union minus 3 to 3, and then union 3 to infinity. So solution is not valid on this interval because solution becomes undefined. Solution becomes undefined on this interval, because when you insert a number less than 3 in this, so square root becomes basically a complex number, so we don't include this interval here in the solution. So the solution is valid only for these two intervals by excluding the singular points 3 or minus 3. I hope you get it. There is a question in the chat. The quiz will be available at 1:25 p.m. So concentrate on the lecture, please. So this was example 3. I hope you got it. If you have any question, you can ask. So we are going to next example now, example 4 of the linear first order ODEs. In example 4, the right hand side f of x, you can see here, the right hand side is, so annotate, yes. The right hand side function is this one, f of x, which is given as a piecewise function. Piecewise function means the function is 1 on the interval 0 to 1, and for greater than 1, the function is 0. Sorry. How can we handle these kind of differential equations? This is what we are going to see in this example. So you can see in this example, this differential equation is already a linear differential equation in the standard form. So we can see that the p of x is 1 by integrating over e raised power integral 1 dx, we get the integrating factor. We multiply the given equation in standard form with this integrating factor, and we can obtain this thing. Now, this is valid for f of x. This thing. Now, as f of x is piecewise function defined on two pieces of the domain, we solve this differential equation for for the different domains. On the left hand side, I have solved this equation for f of x is equal to 1. So whenever we insert f of x 1 here, we get this differential equation. So now integrating both sides, we can get the solution of this one. Now on the other side, on the right hand side, f of x is 0, then right hand side becomes 0, and then again integrating again on both sides, we get this solution. So now we have two solutions. One solution is basically on the interval 1x less than 1, and the other solution, this is valid for x equal to greater than 1. Now this is, you can see that this is an initial value problem. The initial condition is also given, y of 0 is equal to 0, and what we do, or you can say this initial condition help us to find the unknown constants in the general solution. So here we have an unknown constant c1, which is basically a constant of integration, you can say, or this is basically one parameter family of solution, and this is the parameter of the family of solution. Another constant here on this part of the domain, the solution is this, so C2 is another constant. So we have only one initial condition. We have only one initial condition, and we have to find two constants, one in this solution and the other in this solution. What we do, we'll see that at what point this initial condition is defined. It is defined at 0. So 0 is here. So this initial condition can only be used in order to find the unknown constant for this part of the domain, for this solution, this one. So we can use the question in the chat is why RHS is 0, because here you can see that the function is 0 when x is greater than 1. So on the right hand side here, we are trying to solve this differential equation for this part of the domain when x is greater than 0. So that's why we put here 0. So by using this initial condition, we can find this constant only, but not this one, because it is defined at 0, and 0 is basically is a part of this function when f of x is 1 here. So this condition help us only to find C1. Now we can simply use this condition. Let's see on the next slide. We can see this one. Yes. So this is our solution in general, basically. This one for x less than 1 and greater than 0, and for x greater than 1, this is the solution. Now using initial condition, because the solution is defined only between 0 and 1, so less than 0, we do not know what is the type of solution, or differential equation is not defined. So we can only apply the right hand limit here. When x goes to plus 0, y goes to 0, according to this initial condition. So when we put x here in this solution, x equal to 0, what do we get? We get 1 plus c1 into e raised power 0, 1. So what is y? The value of y is y0 of y is 0. So from here we can find c1 to be minus 1. Now the question is how to find this constant C2. Normally, the solutions of the differential equations are basically continuous functions. So using this property of continuity, we will use the condition of continuity at point 1, because there is a break in the function in the solution. There is a break in the solution at x equal to 1. So if we assume that the solution is continuous function at all points of the domain, then we can use the conditions of continuity at x equal to 1 in order to find this constant C2. So this is what? This is the condition of continuity, whether a function is continuous at a point. I hope you know this thing, as you have already studied continuity in your calculus math 101 course. So when x goes to 1 plus, why we have assumed here 1 plus? Because we need to go from we have to use this function. We have to use this function. So when x is greater than 1 means when x goes to 1 from the positive side. So the function must be continuous. This is the condition. So when we take the left hand side, when x goes to plus 1, the function must be what? The function must be this one. And when y is equal to 1, when when x is equal to 1, the function is this one. So so this is basically this function. When x is greater than 1, there is a question in the chat. Shouldn't y of 0 is equal to 1? Why is it so? So initial condition is given. We cannot assume it ourselves. It should be given. Okay. So on the right hand side, we use the above function 1 minus e raised power minus 1, because c1 is negative 1. So after solving this, we can get c2, which is e minus 1. By inserting the value of C2 here, we can finally get this solution, which is the particular solution without the constants. So you can also look at the graph of this function. This is the graph of this function. You can see the function is continuous here. There's a basically here at 1, the function is continuous. I hope you got it. If you have any question, you can ask me. Just raise your hand and ask me the question. So now we are going to discuss another example of first order, linear first order ODEs. Sometimes the given differential equation, for example, this one, dy by dx is equal to 1 over x plus y square. It is not linear. We cannot express it. In this form, dy by dx plus p of x y equal to q of x. We cannot express it. So we again look at the differential equation carefully. The given differential equation, this one. If we take the reciprocal of this differential equation, we can write dx by dy. It's basically we don't do it, but just in order to solve it, we are doing this. We cannot take the reciprocal of any differential equation. It's totally insane. Physically, it is nothing. Mathematically, it is not possible. But this is just a, you can say, hit and trial technique. So dy by dx is equal to 1 over x plus y square. If we take its reciprocal, we can have dx by dy is equal to x plus y square. Now, if you notice here, this is now a linear differential equation in which x is now dependent variable, y is independent, x is dependent here, and here you have independent variable. Now, this differential equation becomes linear in x, linear first order differential equation in the variable x. So now we can solve this differential equation using the linear technique. We find the integrating factor. Everything will be reversed, you can say. Now the integrating factor must be what? Integrating factor must be a function of y. And integrating factor, we integrate this p of y with respect to y. So we must get integrating factor in terms of y. Now again here, multiplying by integrating factor on both sides to this equation, we get a product rule of the derivative with respect to y. And this is integrating factor. Now this is your dependent variable, and we also multiply the integrating factor on the right hand side. Now integrating both sides with respect to x, we get this one, and here on the right hand side we can use integration by parts, and we can integrate it. We add the constant of integration, and finally we get this solution. Now this is your solution, which is an implicit solution. So you can find the value of c as well if we are given the initial conditions. I hope you got it. If you have any question, you can ask me. I'm going to repeat it. This kind of differential equation is what? It is not linear in y, but if we take its reciprocal, it becomes linear in x. So we reverse all the process, or you can say we have interchanged x and y, and now it is basically linear differential equation in x, and then we can solve it using the same technique. There's a question in the chat. Why is it implicit? The solution is implicit. Implicit solution is that solution in which we cannot separate y and x, or you can say that the explicit solution is that solution which is in the form of y is equal to f of x. So this solution is not like that. So it is not explicit. It is called implicit solution. I hope that answered the question. There is another question, sir. Can you explain the integrating factor in this case? Integrating factor in normal case, what is that integrating factor? If you look at this example, here the integrating factor is what? Integrating factor is p of x. P of x. We choose here p of x, and then we integrate with respect to x. Because the equation dependent variable here is y, because the equation is linear in y. Now in the next example, the equation is linear in x, so everything will be interchanged. Now the integrating factor here is what? Sorry. Integrating factor here is what? It should be a function of y, and the integrating factor should be integral p of y dy. This should be your integrating factor here. I hope that answered the question. If you have any further question, you can ask me. Now we are going to, so some of the exercises I have included on this slide. You can have a look and try to solve these exercises for your practice. Now we are going to start another form of the differential equation, which is the exact differential equation. But before discussing exact equation, we need to discuss a couple of definitions and the differentials in two variables. Now, differential of functions in two variables. What is this? You have already studied the differential for single variable in your calculus course. Now we are going to discuss the differentials for two variables. So if we are given any function z, which is a function of two variables, x and y, with continuous first order partial derivatives. I hope you know what is a partial derivative. In the region D of the xy plane, then its differential is, we can define its differential as dz is equal to partial f over partial x dx and partial f over partial y we should have y here, not x. So this should be y. There's a typo mistake. So this is how we define differential of a function of two variables. In a special case, when the function is fx y is equal to c, then df of xy must be 0 because the right hand side is constant, and df of xy can further be written in this form: partial f over partial x dx and partial f over partial y. Here we must have y because it's a typo mistake. So partial f over partial y dy is equal to 0 because the right hand side is 0. So this is basically the basic definition of differential of a function in two variables. Now, in other words, you can see that this is what f of x y is equal to c. This we can write a one parameter family of solution in this way. When we discuss the family of solutions, we discuss that this is how we can write a one parameter family of solution, or you can write g of x y c is equal to 0. This is what? This is one parameter of parameter family of solutions. Either we can write this way or we can write in this way as well, the one parameter family of solution, where c is only one parameter. So if we are given a one parameter family of solutions f of x y is equal to c, we can generate a first order differential equation. We can generate a first order differential equation by computing differentials on both sides. For example, this is a one parameter family of solution, this one. For example, this is a solution of some first order differential equation, and it is one parameter family of solution. Then taking differential on both sides, we can take the differential. Differential is what? First we take the derivative with respect to x of this whole thing, means partial f over partial x, where y will be considered as a constant in this expression. While we take the partial f over partial x in the differential, the x will be considered as a constant. Now, the partial f over partial x of this function is what? X square derivative is 2x, 5xy. The derivative of x is 1, y is a constant, it remains same. And here there is no x, y is considered to be constant. So its derivative with respect to x will be 0. So what we get, it is 2x minus 5 dx. This is the differential, means partial f over partial x. We calculate it from here and then times dx. Now plus here, and partial f over partial y. Here I've already told you that this is y. Partial f over partial y. Now we compute the derivative with respect to y of this expression. Now what is this? While taking derivative with respect to y, partial f over partial y, we consider x to be constant. So if it is constant, its derivative becomes 0. Here the derivative of 5xy, y ka derivative 1, for x remains same, negative 5x comes here, and the derivative of y power 3 is 3y square times dy. So what is this now? This is a first order differential equation of this kind, where this function is m of xy and this function is n of xy. So this is first order differential equation, which further can be written in this form, or this one. This we can write this in this form. So if we are given any one parameter family of solution, we can construct a first order differential equation by using differentials of this kind. I hope you got it. If you have any question, go ahead, you can ask me. Otherwise, we are now going to discuss exact ordinary differential equations or exact equations. We use here the definition of differential. A differential expression, m xy dx n xy dx is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy defined in R. What does it mean? That if there exists some function d f of xy, so that the df is what? Df is m of xy dx plus n of xy dy. So a differential expression, this one, is said to be exact differential if it corresponds to the differential of some function. So if this is the differential, sorry, this corresponds to the differential of some function f of xy, where you can say that f of xy is equal to c is one parameter family of solutions, or it's a function of two variables x and y. Now, you can see in the example 6 that if we have this kind of expression where this is what? This is your m, and this is what? This is your n. So it is m dx plus n dy. We must have dy here. It's a typo mistake. So now, if we have this differential expression, there exists a function, this one, inverse function, this you call it as a f of xy. F of xy here is what? It is 1 by 3 x cubed by cube. So now if you take the differential of this function here, d of f, you can see that you obtain the similar thing here, what we have here. So now this differential expression is basically a differential of some function, this one. So this is what? This is exact differential equation of first order. I hope you understand it. If you have any question, you can ask me. The next is how to basically solve this exact differential equation. What is the procedure, or what is the criteria for an equation, given equation, to be exact differential equation of first order? Now, if we compare 2 and 3, basically, where is 3? This is your 3 here on this slide. This one, this equation. And 2 is where this is your 2, equation 2. This one, this is your equation 2. If we compare this equation with the next equation of that, I'm gonna repeat it. There's a question in the chat. Can you please explain this? I'll repeat it. So we have two equations. One is this one, which is the differential of f, and the next is this one, which we assume that this is your exact differential equation. If we compare these two things, you can see that we can write the left hand side here, and the right hand side is differential of f. By comparing these two things, you can see that m of xy must be equal to this, and n of xy must be equal to partial f over partial y. Here we must have y here. This is a typo mistake. So m is what? M is equal to partial f over partial x, and n of xy is equal to partial f over partial y. If we take the partial derivative of m with respect to y and partial derivative of n with respect to x, then on the right hand side, partial by partial y, and here on the left hand side, partial by partial x. Now, what is this derivative? If f of xy is continuous, then we can write this thing as partial 2f over partial x partial y, and similarly this can be written as partial square f over partial x partial y. So if this thing is equal for both these expressions, then partial m over partial y is equal to partial n over partial x. Any problem regarding the audio? Umar Sheikh, are you listening me? Can you please type here in the chat window? Okay. So, so this is basically the criteria for an equation to be exact differential equation. If we compare the given equation, exact differential equation, or the given equation with this differential of the function f of x, y, then there's a question in the chat, can we swap the places of m and n? No, you cannot. I think, yes, you can change their places, but be careful here. This condition will be changed here. Now, if this condition is partial m over partial y equal to partial n over partial x, if you swap them, then you have to be careful because this condition is very crucial, and we are going to use this as a criteria for exact differential equation. So what is the criteria? Next, we are going to discuss for the exact differential equation. If we are given any differential equation of this kind, mxy dx n plus nxy dy here, there is a typo here. In all the slides, I suppose, just correct it. So the given differential equation of this kind, we call it exact differential equation if partial m over partial y, partial m over partial derivative of m with respect to y, and partial n over partial x means partial derivative of n with respect to x, where we suppose that y is constant. If these two quantities are equal, or if these two expressions are equal, then we say that this differential equation is exact differential equation. For example, if we are given this differential equation, you can see that what is your m of xy? It is 2xy because it's a coefficient of dx. M of xy must be the coefficient of dx, and n of xy is x squared plus 1, and it is always the coefficient of dy. So if you interchange their positions, here you have dy, then if you have dy here, then you should consider it as n. And if you have dx here, then you should consider it as m. So just be careful while selecting m of xy, because m of xy must be the coefficient of dx, and n of xy must be the coefficient of dy. Now you take its derivative, partial m over partial y, means you take the derivative of m with respect to y. The derivative of y is 1 here, and x and all other things remains constant, because you are taking derivative with respect to y, partial derivative. So everything else will be considered as a constant except y. So y derivative is 1, so we get 2x. Similarly, while taking partial derivative of n with respect to x, you consider only x to be a variable. All other variables will be considered as constant. So the derivative of x square is what? 2x, and derivative of 1 is 0 because it's a constant. So now you can see that this is partial m over partial y and partial n over partial x. These two things are equal. They are equal because this is 2x, this is 2x. So this given differential equation is exact differential equation. So this is basically the criteria for checking whether the given differential equation is exact or not. Once we are sure that the given differential equation is exact, then we proceed further how to solve it. Then there's a question how to solve it. Now somebody has a question here. If you have any question, there's a question in the chat window. There is a question in the chat window. Heather Iqbal, can you explain this, please? Heather, you got it? If you have any question, you can ask me. can we swap the places of m and n? Uh, if you swap the places, this condition will be also swapped. Okay, I hope you got it. These are done, sir. Okay. Now we are going to discuss how to solve these kind of differential equations. Okay. How to solve these differential equations if we are sure that an equation, a given equation is exact, then we can proceed to solve these equations. Now, on the previous slides here, you can see that in equation 4 and 5, we will use these equations here while we have compared this m of xy dx and n of xy dy. We must have dy here. When we compared this with the differential of f of xy, we found that m of xy must be equal to partial f over partial x, and n of xy must be equal to partial f over partial y. This is what we have to use in order to solve the exact differential equations. How do we use it? We are going to discuss it here. So here is the procedure of solving exact differential equations. This one, we start with either this equation, partial f over partial x, or we can start with this equation as well, partial f over partial y. Let us start with this equation, partial f over partial x. We integrate on both sides with respect to x, of course, in order to get the f of x. In order to solve the exact differential equation, what is our purpose? Our purpose is to find the function f, as we had discussed this in the previous slides, on the slide one, this one. So you can see that here what we have discussed, what is according to the definition, a differential expression this is said to be exact differential if it corresponds to some differential of some function f of x. This one, as this is your m of x y dy, if we can find some function f of x whose differential is this equation, then this will be the solution of this differential equation. So this is why we are trying to find this function f of xy. This will be the solution of the given differential equation. So now in order to find f, we start with these two equations, m of xy partial f over partial x, or we can use partial f over partial y is equal to n. So we started with this thing, partial f over partial x. We integrated on both sides with respect to x. Now, while if we integrate this thing, partial f over partial x on both sides, if we integrate it with respect to dx, then the integral and derivative will be cancelled and we get f of xy. On the right hand side, we integrate with respect to x. Now, this is an integral which involves two variables, x and y. And while taking partial derivative with respect to x, as in the previous example, you saw here, this one, yes, maybe in this one, we assume that while taking partial m over partial partial y, we assume that y is constant. So if y is constant, then all the terms which involves only y, they will become 0. So now in here, while integrating here, there might be some function of y which becomes 0, and while taking the derivative. So that's why we take here g of y as a constant of integration. I hope you got it. Why we take here g of y? We take here g of y because here the function is, the integral is basically, it is the function of two variables where we assume y is a constant. We assume that y is a constant while taking the derivative here, or on the previous slide you can see that while computing partial m over partial y here, we assume that y is a constant. Y is constant while taking partial derivative. So when we for example, if we have here y square, then the partial m over partial y will still be same, because y square will be supposed as constant and it will become 0. Sorry, not y, x. Here, not here. Here. If we assume that y square is here, so while taking partial n over partial x, the derivative of y square will automatically be 0 plus 0 here. So it doesn't change anything. So whenever we integrate a function of two variables with respect to one variable, for example x, the other variable will be treated as constant, and we add another function of, for example, y is here is supposed to be constant, so we add another function g of y, and g of y serve as the constant of integration, or you can say this arbitrary function of x, because this function of y might have been become 0 while taking the derivative with respect to x. That's why we add here a function of y. I hope you got it. Now we obtain the function f of xy. This is what our purpose was. We wanted to find a function out of this equation, a function f of xy out of this equation, which will be the solution of the given differential equation if we put it equal to some constant. So our purpose was to find f of xy, but we have f of xy here. But what is the problem here? The problem is the unknown function g of y. Now, if we know what is g of y, then after integrating this factor with respect to x, we can have our f of xy. Now we need to find this g of y. In order to find g of y, what we use the other equation, this one. If we take the partial derivative of f with respect to y, we can put that thing equal to n of xy, which is given in the equation. So that's why we take the partial derivative of f with respect to y, the partial derivative of this whole thing with respect to y, and we can put this thing equal to n by using this second equation. I hope you got it. Now, if we take the derivative here with respect to y of this whole thing, we can take the derivative of this thing, and then we can take the derivative of this thing. Okay, and we can put this whole thing is equal to n of xy, where n of xy usually it is given in the differential equation. Now, proceeding further, when we separate the derivatives, when we separate these derivatives on this and this, we can write further this thing, which is given here, partial by partial y of integral m of x y dx plus g dash of y. This is your derivative with respect to y. We can take this thing on the other side. We can write g dash of y is equal to n of this and this. Now we need to find here g of y. What we do here, we integrate this expression with respect to y on both sides. When we integrate here on the left hand side, derivative will be cancelled. Sorry, derivative will be cancelled, and we get integral of n of xy dy, and here we take the derivative, integral with respect to y. So the derivative of n integral with respect to y will be cancelled, this thing, and we are only left with this integral of m of xy dx plus a constant of integration. Now this is the value of our g of y, which was needed. This is the value of g of y, because n of xy is known, m of xy is known in the differential equation. We can compute g of y. If we can compute g of y, then by inserting the value of g of y here back in this equation 7, back in this equation, we insert the value of gy here, we get our function f of xy, which was required. I hope you got it. So today we are going to stop, and now you can see here. Let's do this example, and then we'll start the quiz. We have a couple of minutes. So this is an example. We have the given differential equation, this one, 2xy, and this is your m, and we have already shown that this is exact differential equation because partial m over partial y is equal to 2x, which is partial n over partial x. Now we start with these two equations. We start with this one, partial f over partial x. We integrate it on both sides with respect to x, 2xy dx, and we add a function of y here in order to compensate the constant of integration here. Now we have our f of xy, where it involves a function which is unknown, g of xy. Now our purpose is to find this g of xy by using the second condition, partial f over partial y. If we take the partial derivative of f with respect to y, it becomes partial f over partial y. And then by using this equation, we can put this thing, partial f over partial y is equal to n of xy. Now what is n of xy? N of xy is given x squared minus 1. So we can put this thing is equal to n of y, which is x squared minus 1. I hope you got it. Now we are going to the next slide here. This one, basically, 2xy is equal to g dash of x is equal to x squared minus 1. Now we take this thing on the other side. We can write g dash of x is equal to, g dash of y is equal to x squared minus 1 minus 2xy. And just give me 1 minute, then you can start the quiz. So now we need to find g of y. Here we have g dash of y. What we do here, we integrate with respect to y. The derivative and integral will be cancelled, and here on the right hand side we have to integrate this thing with respect to y. X will be considered as constant, so x squared will be constant. The derivative of integral of 1 is y. Integral of 1 is y, and integral of this thing with respect to y here is x, y squared by 2. 2 to cancel, we get x squared y, x y squared plus a constant of integration. So inserting the value of g of y back into the expression of f of xy here on this slide, which we have completed here. If we insert the value of g of y here, we get the required function f of xy, which is the solution of the given differential equation, this given differential equation. You can see here that by inserting the value of g of y in f of xy plus a constant of integration, this thing, after simplifying, this will be cancelled with this thing, and we get this thing. Now putting this is equal to 0 or some constant, we can find the solution, final solution, which is given by this equation, and we can find, we can separate y in order to find the explicit solution. So this is the required solution of the given exact differential equation. I hope you got it. Now let's start the quiz. I think I'm going to pause the video here.